Hey, Glass. So I wanted to pick up where we left off last time with heaps and then moving into AVL trees. So this time I have gone ahead and I've done the some of the programming work in advance to try and speed it up. But I want to emphasize as we go that software development is an iterative process. It's something that you kind of work at, you churn, and you you keep pumping those legs. It's yeah, it's very much a labor, and it's something that's evolved. And you have to make sure that as it's evolving, and I kind of emphasized this last time, that you continue to remove things that aren't actually in use. That you're always like pruning and cleaning up before you actually share your work with. Not necessarily before you do a code review or before you show someone else what you're working on, but before you check it in and other people start living with this expanded code base, you want to make sure that it's uh, well kept before you do that. Okay, but before we get back into coding, I want to share a concept with you, and I just think it's an interesting thing to think about. And so it's the concept of idempotency, or of an action being idempotent. And so essentially, it means that it's an action that doesn't do anything. It's it's not exactly, it's not strictly the same thing as an identity, but in certain scenarios it can act as an identity. And so I'll cover a small list and we'll get back to coding or whatever. But I, specifically, I had this concept in mind with databases, and I thought, okay, well, that concept actually exists in matrices, and it exists in derivatives and so forth. So we'll do a few examples. So okay. Um, okay, so if you have some number a, right? A, which is and some element of the reals or whatever, then you have e times x equals a. Then by axiom, we have that if a is not equal to 0, then this necessarily indicates that x is 1, that we have this uniqueness of an identity within the real numbers. And that same unique identity actually carries over into the complex numbers as well, so that 1 is the multiplicative identity for all complex numbers, in addition to the real numbers and the natural numbers and the rational numbers and the integers. Okay, so that's not actually a given in terms of all systems, right? So formally, well, yeah, formally we would say that we have an element A from the set R, which is acted on by some right action X, and this action yields the element A, which is that same one we'd spoken of with R, right? So we just used a lot more words, right? Like, well, why am I saying all of that if I'm just talking about the number 1? Like, can't we just agree to say that? Yeah, and when we're dealing with the real numbers, that's exactly what we're talking about, right? But this concept of idempotency, it extends beyond the identity. It's things that you can think of as acting like the identity in certain scenarios, right? So, okay, that's one example. Let's think about matrices, though, right? So, okay, stay with me. Okay, so here we have a matrix which is diagonal, right? And so, this is enough to span the space of R3, right? So it's got 3 column vectors, or 3 row vectors if you prefer, but you should. I want you to get in the habit of thinking of column vectors for the rest of the semester. Okay, so we have this, right? And so now we can again, create some right action. Or we'll use a left action this time. It doesn't matter so much in the real numbers or scalar numbers, but for matrices it does make a difference. And there's this whole commutator thing that is essentially the non-zero-ness or the idempotency of swapping the order of 2 matrices. But it's beyond the scope, right? Okay, so here. Okay, so here we have some left action, right? X, so some other matrix, which is multiplied with A, and again yields A, right? So we know the identity matrix, right? X. Okay, so I guess it went a little bit off the screen here. Let me adjust this. A little more. Okay, there we go. Okay, so we know that if X is equal to the identity matrix, then it holds, right? But that's not necessary for this equation to hold. So it very much depends on our matrix A, and it also depends a little bit on our matrix I, right? So, okay, so if we have this, then I certainly satisfies this requirement, right? Because the identity matrix is going to hold in this operation, regardless of what's in A. But the A-ness of this is satisfied really in this first multiplication, right? So we actually have this on the left, so it's rows times columns, right? So entry 1, 1 is going to be in that first multiplication. This row, right, so from X, the first row times the first column. And so that's actually satisfied even if we have that. And so we get this same result, even though we're not multiplying by the identity matrix. So it's something that in certain cases can masquerade as an identity. We see that in cases where a matrix can act like a function. It is a linear operator. It can move. It can move the values of a matrix in a certain direction. And that's kind of what the concept of the concept of eigenvalues represents. And so eigen is German, I believe, for self. And so the self values, it's the indication of how much a given matrix is stretching the other matrices that it operates on in a given direction. And so if you have a matrix of full rank, so something that's non-degenerate, so in this case it would mean this is a degenerate matrix because you lose information whenever you multiply by it. Although you wouldn't see it from this equation, right? But if you had a matrix full of values and you multiplied it with this, then you would lose all sorts of information. only this if it's a left action, then only this first row is actually doing anything, and so it's you're losing some information on that. So whenever you're in linear algebra and they have you go through all the trouble of identifying the eigenvalues and so forth in doing that, you're kind of building up a certain understanding of of distilling matrices. So there are these like lower level truths about what you're actually doing with the matrices, and you're you're kind of working your way through it while you try to build up the understanding of what exactly it is. But you can think of the eigenvalues and the eigenvectors that they represent, or that they're bound with whenever you reconstruct it, as that representation. So the eigenvector is essentially like it's the matrix that's operating is moving it in this particular direction, right, column by column, and the eigenvalue is how much that scalar stretching is in that direction of the eigenvector. And whenever that represents a derivative, then or the linear operator is the action of motioning forward an object in time by ticking it forward or whatever. So if you have some dynamic system like a pendulum, or something in orbit or something, then that's what the eigenvalues and the eigenvectors represent, or that's what you would apply it to. And so in the x, y, and z directions, it's moving in this direction, this amount for a given amount of time. So you tick it forward in that. Anyway, so that is just another concept, right? But getting back to idempotency, so we've seen that you can get this property, which whenever you're talking about multiplication of real numbers, or of just numbers, right, complex numbers as well, we have this uniqueness of an identity. But again, that's not a given, and that's not even necessarily a bad thing, right? So you can do interesting things with it. So okay, now we've seen this, and we've kind of discussed exhaustively that multiplication can represent an action. It can act a little bit like a function. So I want to show you another one, and then we'll tie it back to databases. Okay. Okay, so Leonard Euler, who is probably my favorite mathematician, he was really the first one to ask this question, right? So of idempotency. So So he wanted to know if there was some function f that you could take the derivative of and get that same function back. And so I imagine that as he was working through the problem, he thought, okay, well, what if f was some constant? So it's true if the constant is 0, because then the derivative with respect to x would be 0 again, because it the derivative of constant is 0. And so it's a trivial answer. So I imagine he went back and forth on it a little bit. But by the time he came around, they already had power series expansion. So they knew about infinite series, just like the geometric series we discussed last time, where you can add an infinite number of values less than 1, and if they go to 0 fast enough, then they actually don't add up to infinity. They add up to some value. So in the case of the geometric series, it added up to 1. And so Euler, among his many contributions, he did some work with infinite series. And so I imagine he played with it a little bit, and he realized that the derivative of a polynomial let's see. Right. So that's an apostrophe there indicating a derivative, right? So you have this polynomial, right? Something of this form. Okay, and so following the rules of derivatives for polynomials, you take the exponent, you bring it down, right, whenever x is raised to some constant power, and you what used to be in the exponent is now multiplied times the previous coefficient, right, and then you decrement the exponent by 1. So this is very familiar. So the derivative of x squared is 2x, the derivative of x cubed is 3x squared, the derivative of x to the fourth is 4x cubed, and so that's essentially the rule that he's applying here. And so he realized that, just through like terms, that he was never really going to be able to make it line up, and so it would take an infinite series in order to satisfy his curiosity, right? So if there was some idempotent differential action on some function, the function that satisfied it would either be the trivial answer 0, f of x equals 0, or it would be one where the infinite series was satisfied. So building up on that, he would construct it where you have the infinite series, and you have the coefficient a sub n times some function on x, so then you would do that, you would do the term by term differential, and you would get this, which is exactly what we had before, but written in terms of summation notation. And again, it's the same problem, but if you had some infinite series, then you could modify this, or you could add the additional requirement that for every term by term, that a sub n times n is equal to a sub n minus 1, and so forth. And so if it's truly idempotent, then repeated application of the differential would hold, indefinitely, so that so that so that the previous term would again be satisfied. You have a sub n times n minus 1 is a sub n minus 2. So that's what you would get after the last one. And so he realized that if he did this over and over again, that until this became x to the 0 and this term became truly a constant, which would be differentiated out the next time, that he was building a factorial function. You can kind of see it here. If you apply it a third time, then you would get n times n minus 1 times n minus 2, and this would carry on until until you reached 1, right? So now he has that each term a sub n tends to tends to 1 over n factorial a sub 0, right? It's just the logical progression of the sequence of this repeated application. And so what this gives us is this infinite sum of x to the n times 1 over n factorial, right? And so given that n 0 factorial is 1, we have and this is exactly e to the x. So this is we got the letter e for this function, for the exponential function, from Euler, and from Euler asking this question about idempotency, right? So what is the idempotent, or the function which allows for idempotent action of a derivative? And it's this, and it turns out to be this profoundly important number in mathematics, and the exponential function itself turns out to be it's an extremely important function. And so the value for e is this series expansion where x is 1, right? So e, just the number e, is is e to the 1, right? So if you plug in f of x where x is equal to 1, then you can compute an actual value for this. Yeah, we'll take a minute and we'll do that in JavaScript. So you'll see that you can do summations in programming. Like you can use you can use Riemann sums, or in the case of infinite series, you can do infinite summations in programming languages, with the caveat that you're going to have an error term. So there's a limit to how close you can get whenever you're using a finite amount of space to represent this infinitely precise value. So pi in any programming language you use is not going to go all the way to infinity, in infinite number of terms, even though it could. E, which is another transcendental, which is it's not a fractional value because it's not rational, but a decimal value, which goes on forever and doesn't repeat itself. And there might be additional requirements as well. I think like it has to, transcendentals have the additional property that they contain every other sequence of numbers in them, right? So somewhere in pi is E, and somewhere in E is pi. Don't think too much on that one, right? But it's essentially they are the most irrational of numbers. Anyway, so you can get an approximation for it, and then you just have to be willing to accept some error term on it. But the wonderful thing about it is because you, through the for loop or whatever you're using to compute it, you can know what your error on that value is. You are the one cutting it off. And then, so your approximation comes with an error term, and you get to decide how good you want it to be. Although if you're using doubles or float 32, to represent it, or so float 32 or float 64 or whatever, to represent your number, then in some regard the system is dictating to you how precise you can get. Anyway, okay, so that's where the number E comes from, and it's this concept of idempotency. And so what does that have to do with databases and, if anything, right? This not directly, right? But the concept of being idempotent. Whenever I was finally given the responsibility to start working with a relational database, I had to make sure that my script satisfied this concept of idempotency. Although I think we use the term SQL safe whenever we were doing it. And essentially, whenever you run automated scripts against a database, if you're going to change the data, then there's a little bit of risk that the script will be executed more than once. And so you need, especially if you're aggregating the scripts into something that may be executed more than once, then it's not enough to just understand the language. You have to push one step further and essentially test that your change whether or not your change has already been applied. And so there's a few ways to do it. One way is to have a table and flag whether or not the script has already been executed, and only execute it if that script ID hasn't already been flagged as having been executed. Another way is to hard code, so let's say you're updating student IDs, and you do it in batch. You have some files, some batch file or whatever. Then you would construct the script in such a way that the modified timestamp for those updates was hard coded, and then as you're performing your update, the students table, right, and set equal to set student ID equal to blah, where the student ID was previously blah, then you would add an additional condition, so and the modified date is before whatever, right? And then you would have something that automatically updates the modified date whenever a change is made to that table, or you would, within that same update statement, so update student ID to whatever, and the modified date equal to whatever that hard-coded modified date is. Then whenever it ran multiple times, you would have that comparison to verify that you're only performing that update if your script hasn't already been applied, or if in the case of using the modified date, if someone else hasn't already come along later, after you were given that assignment or whatever, and updated it manually. You don't want to overwrite their changes if someone else has done something more recently, right? And so it's this really simple concept, and it's something that we would do if you were using human intelligence, right? If you had to manually perform some action, and it's like, hey, go mop the kitchen or whatever if it hasn't been done in the last hour. And so it's not something that's critical. Nothing's going to break if it gets mopped twice in the same hour. But it's a concept as simple as that. If some task has already been performed and satisfied, then don't run it again. Right? And so whenever you're manipulating data, this concept becomes real important. So whenever you get to databases, you think about it. But I don't know. I thought the discovery of the exponential function and the value e was pretty cool. Yeah. Well, we'll do it another time. We're kind of already running long on this example. So we'll jump back into heaps and AVL trees, and if we have time, we'll do like an intro to representing graphs, and if not, we'll cover that next time. And maybe we'll do like numerical integration, which is essentially Riemann sums through programming. But you can really do a lot of cool stuff with integration through programming, and you get used to doing it through analysis, and it seems like something you shouldn't be able to do whenever, like with the programming, but that little dt or dx or dy or whatever, it turns out that is essentially all you need to compute it. It really is simpler to do it numerically than it is to do it analytically, and so once you get used to that, then it's not so bad. Okay, so let's jump back into the code. Okay, so you should observe that we are back at square one, and the sighs of desperation let out across the world. So I have already done this, and we're gonna kind of rework it a little bit. So I know that we're gonna need to add text because we're gonna use string builder, and I'm going to change this a little bit because last time whenever we did it, we used left child and right child, and the concept that a heap is essentially a binary tree, but I'm going to use that implicitly, and we're just going to do node IDs for this. Okay, and so actually here, let me jump back to my whiteboard for a little bit, and we will discuss our strategy here. Okay, so whenever we have a heap, and we're going to discuss min heaps, but it's the same concept, but anywhere, if we were to do a max heap, anywhere that we have a less than sign, whenever testing the value of the node, we would replace it with a greater than sign, right? It's just the comparison operator that you're using. But we'll discuss min heaps, and that's sufficient for the discussion. Okay, so a min heap would always keep the least valued element at the top, and we're going to use numbers. You could use dates, you could use modified date, right? That's a valid example. Or last usage time, last access time, so that if you were to use a min heap for last access time, and if you were to imagine writing your own programming language or your own runtime environment, a managed runtime, where you manage the memory for someone else, then they make a request for memory, and then you would store that, and then one possible solution, throw it on the heap, right, is to maintain the last access time for it, and whenever it's accessed, or you would check through the oldest items first in the heap to see what the last item used was, or the number of references to that particular object. So whenever the reference count for the object at the top of the heap is 0, and you're constantly maintaining your heap every time the reference count is updated, then you would remove it. You could reclaim that memory, and so you could use a min heap to maintain dynamic memory, and save your garbage collector the effort of having to recurse the tree every time that the garbage collector woke up and did its thing. Okay, so with a min heap, you prioritize balance, right? So we discussed it before. We have insert and extract; those are our public methods, and we have sift up and sift down, and those are our private methods. And so insert and extract, first thing they do is they maintain balance, and sift up and sift down, what they do is maintain the priority. And so that every time an operation is performed against the heap, whenever it returns from those public methods, the two conditions that the two promises of a heap are satisfied: the balance and priority. So whenever something is inserted, right, it goes just on the next item in the heap. So row, and then column. So row at a time, and then I guess it's not really column, right? But row, and then further along the row. So row and then peerage, I guess. Okay. So we have a min heap. So everything here, anytime you have a parent-child relationship, the parent should have priority. In this case, priority meaning that it's less than all of its children. And then by the transitive property, it should have priority over all of its descendants whenever it's satisfied. So then, because we're doing this like in typewriter fashion, essentially, so you go down to the next line and then you start again at the left. The next slot would be over here, and we'll insert something that's valid. But right now what I want to show is the equivalence between this and an array. Right? Or I guess I should say a list, so something that's more dynamic than an array. So if we had a list, right, then, and we were maintaining balance, or just ensuring the compactness of it, we wouldn't insert the item 25 at index 10,000. We would insert it at index 0, 1, 2, 3, 4. We would insert it at index 4 in our list. And so that's very clear, and the way we've described how we're maintaining our heap by first maintaining balance and doing it in typewriter fashion, we can create a one-to-one correspondence between the locations in our binary tree, the binary tree that is our heap, and the array. So root would be 0, the left child of root would be 1, the right child of root would be 2, the left child of the left child of root would be 0, 1, 2, would be 3, and so forth. And so it would progress, in that fashion, so on and so forth. But it's 0, 1, 3. You could maintain it so that you're adding the number of items on the row each time you go, but then you have to compute what row you're on, and it's a little more overhead. What would be better is to find a way to go back and forth between the index in your list, right, or in your array, whatever you want to call this thing. Just understand that it's dynamic. It's not as static as an array. Between the index in this list and the location in the tree. And so What I propose is using a one-based indexing system for the tree. Uh, so that whenever you go down a level, the left child of the current node, so when we start at root, the left child would have an ID twice that of its parent. So you just multiply by 2 or shift left by 1 for binary arithmetic. And again, the left child from this first descendant to the second descendant is again multiplication by 2. And that holds even whenever it's not a power of 2. So you can see the right child is going to be 1 greater than the left child. So to get to the right child, you would multiply by 2 and add 1. Or you would compute the left child's index, or sorry, the left child's node ID, heap ID, whatever you want to call it, and then add 1. And so, again, the left child arithmetic holds from here. Right? So the left child here is 6, where its parent was 3, is twice that of its parent, and then the right child is plus 1. And so this is just 1 indexed, and this is 0 indexed. So to go back and forth between them, the ID in the list, the index in the array, the 0-based array, is always going to be 1 less than the node ID. So it's enough to keep the node ID for the node, for the heap node, and then just dynamically compute the index in the list or the array or whatever it is you're going to use there for that. So if it was JavaScript, it would be an array because JavaScript arrays are dynamic. In other languages, it's going to be it'll be a list more than likely, or some equivalent of that. So we have our arithmetic to navigate through, and we know the order that we're doing it. It's in typewriter order, right? So row and then left to right, and then row and then left to right. And it's a binary tree, so no node ever has more than 2 children, 2 direct descendants. Okay, so that's the balance. That's how we maintain balance, and it turns out to work quite nicely. Where if we have this list, this collection, list or array, whatever you want to say, that it appending an item to the heap is in 1-to-1 correspondence with appending it to the list, and it both stay compact if we use this method. But now, if we go to the next one, and we add something that has a higher priority, and in a min heap, higher priority means lower value, then we have to start doing some actions here. So at this point, where we've added something that breaks priority, so we've maintained balance because the first thing we do is add it in the right location, and then we test to see whether or not the second condition is satisfied, and that being priority. So we take a look at our new node, and we would test to see whether or not it violates priority with its parent, and if so, then it needs to swap, and if not, then we don't need to do anything, because thanks to the powers of induction, of mathematical induction, we know that if we have something that already satisfies those conditions, and we maintain balance whenever we insert it, and priority is maintained, then it was already maintained everywhere else. Everything is as it should be if this first test is satisfied. If not, then we have to recursively or iteratively bubble up the item until it reaches its stopping point, until it reaches a point where its parent has higher priority than it. And then at that point, we know that it's satisfied. Right? So in this case, the first thing we would do is swap it with this node. And so there's two ways to do it, and the way that we're going to do it in our program is by moving the node and then swapping the IDs, if that makes sense. So that down here we have ID 4 value 20. So what was formerly this node comes down to the left. It's actually to the left. And then ID 8 value negative 1, because ID and value are going to be coupled together, goes up. And then we correct the IDs. So this becomes 4. And this becomes 8. So that's the order that we're going to do it. And then again, we would have to do it. And you see that negative 1 is going to have priority over 10. And because 10 already has priority over 25, we know that through the transitive property of the totally ordered system that we're using, and that we're comparing numbers, that if A is less than B and B is less than C, that A is less than C. Right? That's we've already worked on that. So that we don't need to test it to its siblings, it's enough to test it to its parent. Right? So transitive property, hooray, mathematics, mathematical rigor, we've already done some of this stuff. Okay, so that's essentially what we're going to do. I'm going to code it a little bit quickly because I kind of want to get to AVL trees. But we'll see. If we don't have time, we'll get to AVL trees next time. But let's see what we can do. Okay, so we have all of the packages that we need. We've included all of our base class libraries. And so we have a class here, and we're actually going to operate under a namespace, and typically we would create a new file for these other classes, but that's not necessary. It's just a bookkeeping thing, so that if you were working for me, I would insist that you create a new file, but because we only have this one page to work with, we essentially have to group everything together. So we're going to maintain separate classes, but they'll still be grouped under the same namespace. And you can think of namespaces in Java and C#. In Java, it's called a package, but the package is going to have a path that operates very similarly. But in Java and C#, you can think of them as directories. So anywhere that you see something with a period, right, then you can think of that as being a subdirectory for this. And in fact, the directory structure of your project would you would have a project Rex tester, and then you would have a subdirectory foo in there, and then any class files, any .cs files that work in the namespace rextester.foo would be in the directory path rextester/foo. Okay. So just a word on namespaces. Okay, so we have our node, and we've simplified it so that now we have a node ID. And I think last time I put some default value, and we'll do that again. We'll provide a default value. And it'll be something that couldn't possibly be achieved and isn't the default value for integers, just to indicate that that it hasn't actually been properly assigned a node ID. If somewhere down the line we want to verify whether or not the node has been added to the heap, a node ID of -1 indicates that it has definitely not. Okay, and then value is going to be whatever is stored inside of our node. So here it's an integer again. If we wanted to use generics, then it would look like this. But for simplicity, we're not going to do that right now. Maybe you will get the chance to do that later on. And then, again, I'm encouraging you that in whatever programming language you adopt as your native language, to get in the habit of creating some printable representation of your object as you go. Whenever you create an object, you should have something that you can call, that you can write out to the console and see, what is going on. It's going to help you, as you're debugging. Okay, so there's not a lot in this object. It's a node ID and a value. So it's a really simple thing to spit out. Okay, perfect. So our node is done. And so now we're going to create our min heap. And again, a min heap means that the highest priority item in the heap is going to be the least of whatever the comparison value is for the nodes. So if it was last access time, then it would be the item that with the minimum last access time. And whenever you're counting time in milliseconds since January 1st of 1970, so midnight, January 1st of 1970, then the minimum last access time is going to be the item that you've forgotten about, basically. So the one that you have waited the longest since you've last accessed it. And then in the case where we're discussing using heaps to manage memory, where you have a reference counter, whatever, then the minimum item would be the item with the least number of references that lives on the heap. Okay, so then we're going to put most of our heap logic in our min heap class, and we're going to keep the heap node as simple as possible. So list is a generic type. In C or C++, you would call them templates, and I'm sure Java has a term as well. I don't know if it's generics or if it's templates. I can't remember. I will brush up on my Java before we do graphs. Okay, and then so we're going to have a private method for sift up. It's going to take a node and it's going to bubble it up until our priority is satisfied. And until we implement that, we're going to throw a new non-implemented exception. We're going to have our public method, which is going to be insert value. And the reason that I'm using the shorthand val instead of value is that in C# value is a keyword, and in particular, if I had public string foo, private string foo, then I would manually create my getters and setters. So get returns foo, set is a function foo equals value. So the keyword is for this case. So we have a function. It's an accessor function. So in Java, you would create get foo. You would create two separate methods: public string get foo, and public void set foo, which accepts the string, and then we're going to do something there, right? So this is implicit here. So just due to the syntax, and we could write it a different way here. C# has a convention that simplifies it because getters and setters are so standard that you're going to need them. And so it simplifies the language. And if you end up applying some logic, like if you're lazy loading stuff, and if we have time we'll discuss what that is, but essentially it's null until you need it, and then you perform whatever expensive operation it is to set it up once, and then once it's done you cache the result and you return the cached result. So we'll get to lazy loading later. But if it's simple, if it's the same as if you just publicly exposed this property, right? If you just made this public, then you use this shorthand, this get and set. And if it's not simple, then you can perform whatever value, and with set, they give you what would be passed in to the setter here with this keyword, this value. Okay. But because it's a keyword, we can't use value here, so we have to rename it. So I'm going to use the shorthand here. Okay, so we have that. It's not implemented yet. We have another private method, which again accepts a node, and is again not implemented. Yeah. Then we have our extract method, which takes whatever the highest priority item is, so the next patient into the ER, and returns that, which is again not implemented yet. Okay, and then we have our toString method. Okay, so we have our heap. Excellent. Okay, so yeah. So we have our toString. So let's go ahead and create that, because I insist that you get in the habit of creating these toString or equivalent methods. Okay, so if our heap is empty, then just return the empty string. And so string.empty is the same thing as this, except that it doesn't ask the compiler or the runtime to create a new memory allocation for an empty string. It just reuses the same empty string, because all empty strings are created equal, and this one has a lighter memory footprint. So that's a good idiomatic habit to get into if you work in C#. Okay, and so then we're going to have a string builder that we use to basically put into place all of the strings and characters that we're going to use when constructing our heap as a string, but we're going to defer the action of actually creating the string in memory until we're ready, so we only create the string once. Okay, so we have our string builder, and navigating the heap is going to be a little bit difficult inside the toString, so we're going to have a helper function. And it's not going to return anything, but it's going to accept that string builder instance. and then it's going to accept some current node and a depth optionally. Yeah. And so these default values are used to create optional parameters. So if a default is provided, then whenever you invoke the method, you don't have to specify it, and if it's not specified, it will take the default value. But they have to be put at the end of the parameter list whenever you're defining your function. And you can have more than one, but essentially as soon as you have one, you can't have any more that are required. Okay, it's not a terrible restriction. So we're going to use a combination of in order, pre-order, and post-order. And we're not going to do it explicitly, but you'll just see. Okay, so we're going to want to precede each line that we spit out with tabs, so that whenever you go down in the tree, it gets tabbed over one more. So for each level of depth that you have, you want to have one more tab, so that whenever it prints out to the screen, it doesn't look like garbage. Okay. Let's see. So we're going to append to our string builder a tab character for every level of depth. And we are going to be reusing this line. Okay, and then we're going to append a line for the current node. So this is the pre-order visiting action. And then we want to tab over for whenever we specify what's going on with the left child. So left node ID is equal to node ID. And we said that to go from parent to left child, it's multiplication by 2 or a left shift by 1, right? So using the node IDs. Right? Okay. And so then we test to see if the left node ID is less than or equal to the size of our heap. And if so, then there's something there. And if not, then it's null. So if there's something there, then we want to append a line, not just left. Right? We don't want to just append a string. We want an inline character at the end. So that's the difference between this and this, is that it automatically tacks in an inline character for you. And then we're going to recursively visit the left descendant. So it's the same string builder. It's going to be the left child, which can be found at left node ID minus 1. Right? So the index of our heap is always accessed by going one less than the node ID. And then we increment the, oh, not increment, we specify that the depth is one layer deeper than the current node whenever we go down a level. Okay, and if it's null, then we append to that. Okay, so now our right child is going to be very similar. Okay, so we have our tabs, and then this is now right node ID. And we said that the right child is always one greater than the left child's node ID. And now we have our right node ID. We test to make sure that that is not null. And this is right. And this will be right. And then whenever we recursively traverse it, the index ID within the list is always 1 less than the node ID. So to access our right child, we have the right node ID minus 1. Okay, so that's the stringify method. ToString, now we can invoke it. We're already testing that if it's empty, right? If count is equal to 0, then we just return string.empty. So then we're guaranteed that there is an element at index 0. Perfect. Okay. So now we can construct our main method. And so as we're building this, we're going to use we're essentially creating a test case so that whenever we finish doing this, if this was a production project, we would create, if it didn't already exist, we would create a test project, and then we would move the stuff that we're about to put in the main method into a unit test. So we're already doing that. We're already asserting that what we're doing works. But we would create a unit test that does essentially the exact same thing, but we would make sure that that it's automated, that it's executed anytime code is updated, to make sure that the essentials of our heap were not violated. Okay, so we're going to create our heap. And then we're going to perform some inserts. Well, let's make sure we can insert one value first. Okay, and then we're going to write it out to the console. And we'll leave a blank line. Okay. And we'll do this later, but first we'll just write it out. And then we'll change hello world to completed. So if we get there, then we at least were able to execute our main method. And we got an error, which shouldn't surprise us because it's a not implemented exception. So we can't actually insert anything yet. So let's go deal with that. Okay. So to insert, we need to create a new node. And we set the value equal to that. And then we add it to our heap. And then we update the node ID, and conveniently it's equal to the size of our heap once it's added. So when we add our first element, we have a count of 1 and our node ID is 1, and then the index is always going to be 1 less than the node ID. So the index will be 0 and our node ID is 1. And it continues in recursive fashion. Okay, and then we're going to want to call sift up whenever that's done. And so we pass in our new node. Should be new node. And then we return our new node because we made a promise that we would return a heap node. Okay, so we insert it at the end of the list, right? So we're just adding it, we're appending it to our list. We set the node ID correctly, and then we call sift up, and sift up is going to handle all of the logic. So balance, and then priority. Okay. So now let's deal with sift up. Okay. So the first thing we're going to do is compare it to its parent. well, the parent node ID is going to be equal to the right shift of the child's node ID. And so this is true whether it's right or left. So the left child is going to be an even number, the right child, because it's a power of 2, unless it's root, but you know, whatever. And so the left child will be an even number, and the right child will be an odd number. And so that right shift, if it's an odd number, if it's the right child, well, that 1 gets dropped off, and it becomes equal to its left sibling whenever that's right shifted. In particular, let's see if we can. 3 shifted right is the same as 2 shifted right. Okay. Okay. So, right. So the parent ID is easy enough to get. We're gonna enter into a loop here. But first, we're going to default parent node to null. And so long as our parent node ID is not equal to 0, so we haven't right shifted off all of the values, then we can access it. So if it's greater than 0, right, and we could have equivalently said, as long as this is greater than 0, then there's something, then we can translate between node ID and index and expect to get something. So then we've got the parent node. If the sifting node has higher priority, then swap it with the parent. And we're using less than here because it's a min heap. Right? So that's how we measure priority. And it's a swap, so just like if we were swapping variables, we use a temp. And in this case, the ID is the temp. And then this, the pupil has become the master, essentially. So the parent node ID for the next iteration of our loop is going to be, again, that same right shift, right? So node.node ID shifted right by 1, and then we'll test the next level. And then whenever I'm writing loops, as you've seen, it's very easy to write an infinite loop. So I like to be explicit and say that if I've entered into this block, then I actually need to run the loop again. So rather than letting it carry on, I explicitly say I want it to go back to the beginning of the loop again. Test the next condition and see whether or not you can iterate it. So basically that we're not already at the root. And if so, execute again. And then I'm explicitly stating that if you reach this line, if you reach the end of the loop, then break. Like you didn't have to do anything. And so when does that happen? So if there wasn't a swap, if we sifted up and we realized, oh well, the parent actually is supposed to have priority over this node that we're letting bubble up the tree, so then we don't need to do anything anymore. And so in that case, we can just break the loop. So the natural end is if it bubbles all the way up to root, which is tested here, and then the short-circuited end is if we encounter something with higher priority. We went in and we have a blister in our finger in the emergency room, but we have encountered someone in front of us that was stabbed or shot or something, right? They're going to need to get treated first, so we don't actually bubble up the emergency room priority list in that case. Okay. So then we've implemented. Now let's run it again, see if we can execute. Hey, we reached the end, so we can ask more of our program now. Okay, so now let's see if we can insert two things. Great. Okay, so we have our initial child and we have our left child, and it's bubbling correctly. So then we should be able to insert anything we want now. It's the extract that we've yet to implement. So let's test that hypothesis. Okay, so then we'll just fill it up with other stuff. 15. And then we'll insert something that is definitely the minimum value by going negative. Okay, so we run it. Is our representation correct? So the highest item, the one with highest priority, is -10, right? So it's the minimum value in our list. The next node, so we're not guaranteed that they'll be sorted necessarily by node ID, but we are guaranteed the parent-child priority relationship. So this is less than both of its children, so 2 and 3. So -10 is less than 5, and it doesn't have a right child. And then, no, sorry, it does have a right child. So -10 is less than 5, and it's less than 15. And then 5 is less than 10. Perfect. Everything seems to be correct. So now let's test extracting. Okay, so we could do this. Well, I mean, it's not strictly necessary that we do this here in the test block, but I want to expose you to the different ways that we can do this. So the assignment equals actually does return a value if you don't semicolon it out. So that will assign to next node, and then the value that was assigned there is actually the output of this larger parenthetical here. And extract, we would expect to return null whenever the heap is empty, or something that's not null whenever the heap is not empty. So this is valid syntax, and it's saying I want to do the assignment and the assignment and the test in one line. So it's valid. It's been valid since C. Most languages allow that. This is valid in JavaScript, C, C#, C++. It's possible that some languages have outlawed it because they're not fans. But for the C-style languages, I believe this is valid. Okay, so then within our loop, we're just writing debug statements essentially. So we want to indicate what it is that was extracted. We're going to use our interpolated strings because I am a huge fan of interpolated strings. It formats so nicely, right? And you don't have to do the sprintf stuff and indicate what the value is and so forth. Not that there's anything wrong with that. But it's a fair amount to remember to print something to the console. Okay, so then next heap state. And we'll just do this while we're debugging. We can remove it later. Ran into another not implemented exception. Those do tend to come up. And uh, looks like we won't get to AVL trees, which is a shame because we spent a fair amount of last class working on this, but that's fine. Well, it's fine. It's important to review data structures a bit. And I would like, there's not going to be a homework assignment this week, so that's a little bit my way of making it up to y'all that we don't, that I've gone over on my time pretty regularly. But whenever I provide a file to you, if you're going to explore it, I would like for you to either essentially transcribe it or translate it. So look at the file and write it out. Like if it's C# and you're trying to learn C#, then transcribe it. Go through the motions, have it break on you a little bit, and work through it, and you'll learn the language a little bit that way. Kind of, I like to think of it the way that the monks used to transcribe. They would copy books by hand, character by character, just laboriously, and they were the most literate people in the world during those times, and there's still something to it. It's it is effort. It's more than not doing it in terms of effort. But it's the easiest way, I feel, to pick up a language and then also to pick up the concepts as well. So you'd be surprised how many tiny mistakes, like how many minutiae you miss as you're copying something that's right in front of you whenever you're learning these languages. And it's just these little things that we're blind to, that we don't expect to see, and therefore we don't see them. And the compiler is very rigid, and so it'll insist that all of the syntax is correct, and if you don't have it exactly right, then it's going to break, or then whenever it's running, then it won't execute. And that action will reinforce what it takes to learn the language. So I feel that transcribing it is a very important part. Whenever I provide these files to you, that it already works. I tend to test my stuff at least a little bit. So you can do that, and you can pick up the language and the concept at the same time by doing that. And then if you're trying to pick up a new language, then okay, if I give you the file in C# and you want to learn Java or Go or whatever, then you already have a lot of what you need. You have function names, you have classes, you have test conditions and problem setup. In that case, it's translation rather than transcribing. And so you take something that you know to work, and then you adapt it, or you translate it to this new language. And so you're essentially copying these concepts into a new language. And that way, if you're already proficient in something, then you can tack on additional languages. But that's kind of, I guess, as you get a little further along. So when you're first learning, it's nice to get that exposure. But I would argue that really you just need to learn, well, I don't want to limit you by any means, but, yeah, just practice. The language doesn't really matter. Eventually they all kind of start to look similar because it's flow control. It's all branch points, if statements, else if, switch statements, subroutines, that is calling a method. Once you get more advanced, creating another process, writing something to a socket, blocking on some input from some other socket. The patterns are very finite, so you don't have to learn everything that there is in programming, or that you could possibly do. You learn just a set of tools, and it essentially spans the space of what can be done. And that set is much smaller than you think. You're actually, just by starting out, you're a lot closer than you think to mastering. So yeah, just find productive labor, and you'll get there. Okay, so with extract, we're finding what the last item in our heap is. And if the last item, the last node ID is 0, and that last item is ID is equal to the count, then our list is empty and there's nothing to extract, so return null. Otherwise, then we're extracting the item with the most priority, and then we're replacing it with the item that's just at the end of our list, and then we're going to sift that one down. Okay, so we've taken the item at the end of our list and we've moved it to the front, and now we're removing that item at the end from the end of the list because we've moved it to the front. So our list actually shrinks by 1 whenever we extract. And if our heap isn't empty, if we didn't extract our last item, then we call sift down with that item we moved to the front of the line. So we put it there at the front, and then we say, okay, well, I need to figure out where you actually go. And figuring out where you actually go is here. But putting it at the front is kind of a placeholder action. So, okay, we moved you to the front of the line. Now we're going to figure out where you go, bub. Okay, so sift down. So we're going to use some variables inside a loop, and just because I learned on C and C++, I'm going to declare my variables outside of the loop. That way they're not created each time the loop iterates. It's possible that an optimizer would actually move it outside of the loop whenever you compile. But you know, it's also good to be aware of what's going on. So we're going to intentionally create an infinite loop here. And we're going to need to remember to either return from our function or break the loop. Okay, and those are essentially the same thing because there's not going to be anything after the loop. Okay, so our node ID, which was declared up here, the current node ID, is equal to node ID, so the sifting node. The left child is multiplication by 2, or shift left, and the right child is always 1 greater than the left child, because we're doing this in typewriter fashion. Right? Rows, and then from left to right. And then just a note on comments. So the better you get at programming, the more you'll realize that comments aren't just for people that are new to programming. It is how you keep your thoughts straight. So hopefully your variable declarations will all use meaningful variable names and so forth. But the comments are going to be how you make sure that you haven't made some bonehead mistake whenever you were, rather that I haven't made some bonehead mistake as I'm going along. Not to imply that anyone else ever makes one. But also, whenever people come along behind you, they're going to want to understand what it is that's going on, and rather than having them construct this entire test project or test suite to figure out all of the cases that your function handles in terms of input and what gets mapped to what, and then seeing what it's logically equivalent to. Sometimes it's nice to just have it in the comments to say, okay, this is what I'm trying to do. And if it's not doing that, then it's a bug. You don't need to, spend hundreds of hours trying to figure out what it's doing. Just see whether or not it's doing what I am declaring in the comments. Okay. So here, if our node ID exceeds the number of items in our heap, then it's essentially trickled all the way to the bottom of the heap, and we don't need to keep looping, so we can return at this point. And it's going to be the same thing for the right child. So if it's not null, and so if we didn't return, then there was a left child, and then that becomes our test node. And then we see whether or not the left node or the right node, the left child or the right child, actually has priority claim. So now we're testing them against each other. When we're trickling up, we use the transitive property, but when we're sifting down, we don't have that privilege. We don't know. It's so we have to compare them directly. So first we see whether or not the right child is null. If the left child is null, then because we're going row by row and left to right, if the left child is null, then the right child is null, and we don't need to test anything. If the left child is not null, then we have to see if the right child's null, then we only compare the item that's falling through the heap with the left child. And then if they're both not null, then we see which item has priority, and the one that has priority takes the spot of the parent and swaps places with the item that's falling through the heap. Okay. And if the right child is not null and its value is less than the left child's, and we use the opposite test. So here, if we'd exceeded the number of items in the heap we returned, here we don't do that. We only see whether or not we need to update the value of test node and make it the right child if it has priority over the left child. But because there's already a left child, we know that we need at least one more comparison. So we're not exiting the function in that case. Okay, so whether it's the right child or the left child, we're going to see whether or not something ought to have higher priority. In that case, in a min heap, it means a lower value than the node that's falling. And if it did, if there was a priority correction, then we do the same swap that we did whenever we were sifting up. And again, we explicitly continue, and again, we break if we reach the end. Because it means that, well, we didn't return, And we haven't exhausted the list, which is when we would return, as if it's fallen all the way to the bottom. But we reached a point where the node had priority over both of its children, or its only child, if that's the case. So if that's the case, it doesn't need to fall anymore, and we break the loop. Otherwise, we make the swap, and we test again to see whether or not it needs to fall another level. Okay, so then now that's basically it. Let's run it. Okay, we're not getting any more exceptions. We're spitting out a lot of stuff here. Right? So this is it once the tree is constructed. And then here, this is pretty noisy, so let's comment this stuff out. Okay, so this is it once it's inserted everything, and then we run extract, and we get -10, 5. Well, it should be in order as we extract. -10, 5, 10, 15. And it's always the top item, node ID 1, whenever it comes out. So it's being updated. If you want to see if all of the intermediate values of the heap are correct, then you can uncomment these lines, and it'll show you after each extraction, what the current state is. So it extracted it, and then what was left behind. So it extracted -10, so then 5 moved to the top. I had a left child of 10 and a right child of 15. Right. So those were the 4 values. Okay, so that's it. I will post this file so that you can compare. And again, I highly encourage you to transcribe it, or if you are focusing on a different language, to translate it into a different language, either C or C++ or Java or JavaScript or Go or whatever it is, whatever language it is. If there's one that you're passionate about, then practice that. If there's one that is assigned to you for other class purposes, then yeah, you should probably practice that one, so you're making sure you're passing your classes. Okay, that's it. Sorry I've gone so far over. Again, no homework this week, so at least you have that. And then whenever we resume on Thursday, we'll do AVL trees, and that'll be in JavaScript. So AVL trees, it's named after the guys that invented the algorithm. They are a binary search tree. So with heaps, the emphasis was on something that was balanced, and then there's this concept of priority. Binary search trees, if you were to do an in-order traversal of the tree, it would be sorted. So that's one property. And then they also provide balance, so that whenever you insert a value into the binary search tree, it's balanced. And then yeah, so those would actually be represented more with a tree. Here we used a heap, which obeys certain tree structure properties, but because of the compactness of it, we were able to use a list or an array if you're using JavaScript. And we were able to bypass having left and right children, and instead deriving the location in the list in a way that is compatible with just using a node ID, and then that provides certain rules that we were able to take advantage of. In that the node ID was left shift and right shift in order to move up or down a level, and so forth. Okay, so if you're not sure what I said at the end, feel free to watch the video again where we cover the whole thing. Okay, I will see you all on Thursday.